we present multi-objective graph heuristic search for terrestrial robot design. Our goal is to efficiently search for the Pareto optimal robot designs in a combinatorial grammar space for multiple conflicting objectives. We propose a multi-objective graph heuristic search algorithm, or MOGHS for short. In each episode, our method starts with a design phase where it first randomly samples a preference weight and tries to search for an optimal design under this preference trade-off. Then, the algorithm samples from the grammar, starting from the initial symbol. With each partial design, we use a graph neural network-based universal heuristic function to predict the preference-aligned optimal terminal design, providing the best rule to be taken at each step. Such a prediction guides the algorithm to prioritize more valuable branches in this combinatorial search space. Our algorithm takes an epsilon-greedy strategy to allow the algorithm to gradually transition from exploration to exploitation. After we sample the design, the algorithm evaluates the sample design under a model predictive control to compute the reward-based objective and updates the design buffer. Finally, we use all evaluated designs to further improve the heuristic function and complete the episode. Here are some results. First, we'd like to show a toy example. In this problem, the first objective is the complexity of the design, which is simply inversely proportional to the number of limbs. The second objective is the height of the robot. As visualized here, our algorithm is able to find a wide spectrum of robots, from the simplest single-cell robot all the way up to a complex but tall walker. Next, we'd like to use a more sophisticated example to demonstrate the efficiency of our algorithm. In this problem, the first objective is to navigate the slalom-like walls as quickly as possible, and the second objective is jumping height. Here in the left figure, we show the searching efficiency of our algorithm compared to other algorithms. Here, HV is the hypervolume of the optimized Pareto front, and in the right figure, we show the Pareto front discovered by the different algorithms. As can be seen, our method is not only able to find better performing Pareto optimal designs, but is also more efficient than the baseline algorithms. Here are two robots discovered by our algorithm, whose structures are well designed for jumping but don't allow them to move forward. Next, we show a robot which has two strong legs that allow it to jump. Meanwhile, the green revolute joint helps it to move forward slowly. Here's the optimal quadruped design for walled terrain tasks. It is suboptimal for jumping tasks due to its heavy body and relatively weak legs. Next, we show another interesting example. Both objectives are for flat terrain locomotion, but one with normal motors and the other one with weaker motors, which highlights locomotion in scenarios where power must be conserved. The best robot in the weak motor scenario has shorter legs, since the robot is unable to balance if the legs are too wide, due to the increase in gravitational torque on the torso. However, longer legs lead to faster strides for the normal power state robots. As a result, the best performing robot in the normal motor scenario has extremely long legs, which at the same time makes it unmovable in the low power state. Finally, we demonstrate a three-objective problem to show the generality of our method. In this problem, we have the flat terrain locomotion task and the jumping task as before. Furthermore, we have a third task, which measures the robot's ability and agility around the vertical axis. The results show that our method outperforms the random baseline algorithm. Here is a robot design discovered by a method which is not optimal for any objective, but has equally good performance on each of them. Finally, here are two interesting human-like robots found by our algorithm, which have high rewards on spinning tasks. Thanks for watching.